Okay, welcome to lecture 33. So we're still learning about plane autonomous systems here, but now we're going to learn about stability and an introduction to classifying critical points of linear systems. Okay, and I guess an important distinction here is, the classifying critical points of linear systems is going to be different or slightly different to classifying critical points of nonlinear systems. So we have to keep that distinction in mind, but today we're just going to be working with linear systems. So again, a bit of revision from a couple of classes ago. If we have the plane autonomous system, so the right hand side does not depend on t, so we have an autonomous system. Dx by dt equals f of xy, dy by dt equals g of xy. Then we can write dy by dx is equal to dy by dt divided by dx by dt, which is just equal to g divided by that function g divided by that function f. And just recall that this is called the phase plane equation. Okay, so in an earlier class we solved the phase plane equation for a linear system. Let's just have a quick just by way of revision, but let's also just look at a nonlinear equation. So you can see this is quite a nonlinear system. We've got a y squared, we've got an exponential of y, we've got a y times an exponential of x. So dy by dx is just again equal to g, so this right hand side of dy by dt, divided by f, which is y squared e to the y. Okay. And of course, there's a common factor of y here, so I can simplify that equation just by dividing through by y. I get e to the x minus 1 divided by y times e to the y. So as it turns out, this equation is separable. So I can multiply through by this denominator, and I get the integral of y times exponential of y times dy equals the integral of the exponential of x minus 1 times dx. Okay, so the integral on the right hand side is pretty easy. You should be able to do that with your eyes closed. But the integral on the left, we have the product of two functions of y. We have a polynomial y, and we have an exponential of y. So quite often, if we have the product of two things, two different types of functions, then we're going to use integration by parts. Okay, and I'm just going to go through this very quickly because, this is something you should be able to do. If we use integration by parts on this problem, this integral becomes y times e to the y minus the integral of e to the y, which of course is just y times e to the y minus e to the y plus some integration constant. So the left-hand side, solve using integration by parts. It's not a particularly hard one, so maybe you might like to pause this video and go and just convince yourself or prove me wrong, one of the two. But the right hand side, as I said, is very easy, so you should be able to evaluate that one. So I can set the left hand side equal to the right hand side now to solve this equation. I'll just combine those two constants into a single constant. So let's say c2 minus c1 equals c. We just got there's just a constant, and so the solution to this phase plane equation is this very non-linear function here. Okay, so that was just to show that even if our autonomous system is non-linear, that we can still solve the phase plane equation and approach this problem in a similar way that we did in the previous classes. Okay, but the thing I really wanted to focus on in this class is classification of critical points, okay? In fact, classification and stability of critical points. So we're going to have quite a few definitions in this class. My suggestion is that you make a list of the different types of critical points and sort of understand what they look like. So the first kind of critical point we are going to look at is called a center. So a critical point, so I'm calling this P0, is just standing for a point. So this point P0 is a center of a system if all the trajectories near this point are closed trajectories enclosing this point. Or in other words, it looks like this. Okay, so we have this point P naught, and all the nearby trajectories are just circling P naught, and they are periodic trajectories. So they're just, it's kind of like, you know, the sun's at the middle of the solar system. Each of these are describing trajectories of all the different planets in the solar system, and they're just orbiting this point here. So this type of critical point we call a center. Okay, so there's your first definition, a center. Okay, the second type of critical point that we're going to define in this class is called a saddle point. Okay, and we've seen multiple examples of saddle points in this class already, and I've alluded to that, but I guess this is the first time we've really defined what a saddle point is. So a critical point, okay, remember if I'm saying a critical point, that means at this point dx by dt equals 0, and at the same time dy by dt equals 0. So critical point, both the ODEs equal 0 at that point. So a critical point P naught is a saddle point of the system if there are trajectories orientated towards P naught, in other words pointing towards the point, and if there are trajectories that are orientated away from P naught, so pointing away from P naught, such that every other trajectory is asymptotic to T1 and T3, or T2 and T3, or T1 and T4 and T. Okay, well, I think it's easier to see just by plotting. Okay, so we have four trajectories here. T1, which is moving towards this critical point P naught, T2, which is also moving towards T naught, T3 and T4 are moving away. Okay, so in this case, yeah, well, okay, well I should use the color. T1 and T2 are orientated towards P naught, the critical point P naught. T3 and T4 are orientated away from P naught. Okay. All the other trajectories move along those asymptote towards those lines, right? So if we start at this point here, we follow the T naught path, but we move along T3 because T2 moves towards the critical point, but then T3 sucks us away from that critical point. Okay, and similarly up here, T1 moves us towards that critical point, but then T3 sucks us away from that critical point. T1 moves us towards the critical point, but T4 moves us away. But the real key point is that a critical point, which is called a saddle point, some trajectories move towards the critical point, some move away. And in fact, 2 and 2. 2 move towards, 2 move away. Okay, the third type of critical point, if we have a critical point P naught, so dx by dt and dy by dt at this point equals 0, both equal 0. So if the third kind is a spiral point. Okay, so this is if there is a circle around the critical point P naught, such that every trajectory within that circle at some time t spirals about P naught infinitely many times, and either approaches P naught or spirals away from P naught. Okay, so there are two cases here. We've got a spiral point which approaches the critical point, or a spiral point that moves away from P naught. So, well, let's have a look. So the first type is one that approaches P naught. So if we start, you know, somewhere out here, then our trajectory just brings us around the critical point in a circular fashion, but we spiral into the critical point. It's kind of like a black hole. I like to think of it as a black hole. You know, if I was out here in my spaceman suit, or my spacesuit, and there's a black hole here, I'm going to orbit this black hole, but I'm going to get sucked in until I'm destroyed. Okay, but the other kind of spiral point is one that spirals away from P naught. So if I start near P naught now, maybe P naught is repelling me, so it could be some kind of magnetic repulsion or something. So I'm spiraling around P naught, but I'm getting further and further away from P naught at every stage. So a spiral point can either be sucked into the critical point or pushed away from the critical point. But as the name suggests, you're always spiraling around the critical point. Okay, so the fourth type of critical point that we can see, critical point P0 is called a node of the system if it is entered or exited by an infinite family of trajectories. Okay, so again we've got two cases here. We've got the case where we have a critical point, and no matter where we start near this critical point, no matter where you pick as an initial condition around this point, you get sucked into the critical point. So this, if I get sucked in, it's like a sink, you know. If you've got a sink full of water, you've just done the dishes, you pull the plug out, it doesn't matter where the water starts in the sink, it's always going to be pulled towards that point, the plug hole, right? So a plug and a sink is like a node. Okay, and there's another example of a node. It doesn't have to be symmetric. They could look like this, right? So every trajectory around this critical point P0 is getting sucked into the critical point P0. Okay, but you can also have critical nodes that repel every trajectory. Okay, so for example, this node here. This is a critical point here, and it is a critical point is called a node because every trajectory, if I start near the critical point, I'm going to get pushed away from it. Okay, so and not necessarily in a linear fashion, but it could be linear. Okay, right. So now we've defined. I think there was 4 types of critical points. We had center, we had a saddle point. We had a spiral point, and we have a node here. I want to define something to do with the stability of each of these critical points. Okay, so a critical point P0 is stable if trajectories which come near to it at some time remain near it at future times. Okay, so this can take 2 main types. So the first type is, well, if we start near this critical point, we get sucked into this critical point. So, for example, the spiral here is stable because we get, no matter how, as time evolves, we get closer and closer and closer to this critical point. So we become stable because we end up at a stable point. Okay, it doesn't matter where I start in this domain, I'm always going to get sucked towards that critical point. Okay, so it's a stable critical point. However, if we looked at a saddle point, okay, some of the trajectories move towards the critical point, but some of them move away. Okay, so this saddle point, even though some of them, you could say some trajectories are stable, some of them are unstable because we get repelled away from this critical point through other trajectories. So we call this an unstable saddle point here. Okay, another kind of stability would be the center. So if I just really quickly cruise back to the center plot here, where are we? Okay, so this center here is also stable because even though we're not getting sucked into the critical point, we're never getting. We always stay close to the critical point, right? So a center is stable as well. Okay, so let me go back to the slide I was on. Right, so okay, so we have another classification here. So a critical point P0 is asymptotically stable if it is stable, so we always stay close to the critical point, and also there is a circle about P0 such that every trajectory inside this circle approaches the critical point as t goes to infinity. So here is the difference. This spiral is actually asymptotically stable because no matter where we start in a region, we set a circle, but in some region around this critical point, we always get sucked into the critical point. So we always end up at the critical point. So we say it's asymptotically stable. However, a center, we always stay close to the critical point no matter what trajectory we're on, but we do not get sucked into the critical point. We just orbit the critical point. So this is not asymptotically stable, but it is stable. Okay, so asymptotically stable, we get sucked into the critical point. just stable, we just stay near it. So the center is actually the only critical point which is stable, but not asymptotically. The center is the only critical point which is stable, but not asymptotically stable. Okay, all other stable critical points, so a stable node or a stable degenerate node, which you don't know what that is yet, a stable spiral point, are asymptotically stable. Okay, so what we want to move towards now in the, well, I'll set it up in this lecture, but we'll actually learn the method in the next lecture, is how do we tell if a critical point is a center or a node or a spiral point or whatever? How do we tell that? Okay, so we're going to consider the linear system. So again, we're going to focus on linear systems at the moment. We're going to focus on critical points of linear systems. We will deal with nonlinear systems in a future class. So if we have this linear system, A, B, C, and D are constants, real numbers, we can write this system, as you recall from Unit 4, in matrix form as x prime equals A times x, where A is the matrix of coefficients, A, B, C, D, and x here is the vector of dependent variables x, y. Okay, so the critical points of the system, of course, are where A times x equals 0. So if the x prime has to be equal to 0, the matrix product A times x has to equal the 0 vector. So A times x, in this two-dimensional case, has to equal 0, 0. Okay, it turns out there's only one point of a linear system that can be a critical point. Okay, and that is the origin. So the only way for us to have a critical point in a linear system is if x equals 0 and at the same time y equals 0. Okay, so a linear system, this is not the case for nonlinear systems, but for a linear system we're always looking for a critical point at the origin. Okay, and in fact there always is a critical point at the origin. Notice this is a homogeneous system of equations. That doesn't hold for a non-homogeneous system, but we're not going to deal with those. Okay, and also determinant of A must be not equal to 0, because if the determinant of A was 0, we actually have infinitely many solutions along one of the axes, but we don't want to deal with that, because that's not really a critical point. That would be like a critical line. Okay, yeah, so as I said, if the determinant of A was equal to 0, there are infinitely many solutions, so you have a critical line. We don't want that. So for our purpose, we'll only consider linear differential equations whose coefficient matrix is non-singular, i.e. A is invertible, it has non-zero determinant. Okay, so the origin is the only critical point. Yes, the origin is the only critical point, basically, is what I'm trying to say. And the determinant of A is not equal to 0. Okay, so determinant of A is not equal to 0 implies that 0, 0 is the only critical point of our system. I want to just define two things here. So this tau here is going to be the trace of my matrix. So the sum of the top left and bottom right, A and D. So the trace of my matrix A. And this capital delta is the determinant of A. Okay. So we can solve the characteristic equation to find the eigenvalues of matrix A. So this is again just as we've done in previous classes in Unit 4. And if we do that, if we take that determinant A minus lambda times D minus lambda, A minus lambda, D minus lambda, minus B times C has to equal 0. Okay, well I can expand this bracket as to make it quadratic for lambda. And so my I guess characteristic equation for this plane linear system of equations is like so. It's given like so. But notice A plus D is equal to the trace of the matrix tau, and AD minus BC is equal to the determinant of the matrix delta. So I can write this equation like so. Lambda squared minus the trace times lambda plus the determinant equals 0. Okay, and therefore I can solve that using the quadratic formula for my two solutions, lambda 1 and lambda 2, is equal to the trace of the matrix plus or minus the square root of the trace of the matrix squared minus 4 times the determinant of the matrix over 2. Okay, well this relationship only holds for the 2 by 2 system, not for the higher order system like a 3 by 3 matrix. Okay, so if determinant of A is not equal to 0, the only critical point of the system is 0, 0, and the nature of the critical point depends on the eigenvalues that we find here, lambda 1 and lambda 2. So the eigenvalues can either be real, unique, and of the same sign. They can be real and equal, so a repeated eigenvalue. They can be real and of the opposite sign. We could have complex conjugate eigenvalues, and in a very specific case we could have complex conjugate eigenvalues with 0 real apart, so in other words pure imaginary. Okay, and so each of these 5 cases is going to affect what kind of critical point we get and what is the stability of that critical point. Okay, so in the next few classes we're going to talk about well, if we have a planar linear system of ODEs, the critical point is always going to be 0, 0. We want to classify that critical point based on each of these 5 potential cases, each of these 5 potential mixtures of eigenvalues of the matrix A. So I'll see you in the next class, and we'll solve that there.